Hey students, lesson 7.7 here. In this lesson, we're going to learn about exponential growth and decay. You will be able to model exponential growth and decay from problems. All right, go ahead and do the review here, and I'll check back with you. All right, here's the concepts we're going to use. Function y equals a times b to the x, where a is greater than 0 and b is greater than 1. Models exponential growth. So the important thing here is b is greater than 1. Now, a little more information here. The growth factor. You can get the growth factor by doing 1 plus the growth rate as a decimal. All right, and then exponential decay, same thing, only notice that b is between 0 and 1, and you can get the decay factor by taking 1 minus the decay rate, written as a decimal. All right, go ahead and do 6 and 7. Decide whether you think they're growth factor or decay factors. All right, so let's see how this works here. Suppose population of deer in a region was 3,500 in the year 2000. Since the population has grown by 3.5% annually, what will be the approximate population in the year 2020? Okay, since we're growing, the first thing I want to do is get the growth factor. Let me rewrite that. Growth factor. And remember I said that it'll be 1 plus the growth rate. And the growth rate is 3.5%, but that's not written as a decimal. To get it written as a decimal, just divide it by 100. And when you do that, you get 1.035. Okay? You also need to know the initial amount. That's the A part of the equation. And that's the beginning population, which is 3,500. Then you also have to know how many years of growth, and that's the exponent, which is, we'll just call that x. Oh, and the growth factor is the v. And so x is, in this case, 2020 minus 2000, which is 20 years of growth. So now we're just going to substitute into this growth equation, exponential growth equation. Our y is our answer. Our a is our initial amount, which is 3,500. Our b is our growth factor, which is 1.035. And that means we're going up by 3.5%. And then our number of years is x. So we need to put a 20 there. And then we're just going to take our calculator and evaluate that using the caret key. And if we do that right, we should get 3,642.5. But since we're talking about deer, we're going around that to the nearest whole number. So we'll say about 3,622 deer. Go ahead, you try that. All right. One application of exponential growth is balance in an account, or the balance of something that earns money over time. And we can have something called compound interest, which means the interest is figured out at more than a yearly basis, like it might be monthly, or it might be quarterly, or it might be daily. And this is the formula, and it really comes from our A equals a times b to the x. It's just that there's a little more details about how you find b there. The annual means per year, right? That's R, N is the number of times in a year that it's compounded. Like if it's monthly, then that'd be 12 times a year. If it's daily, it would be 365 times a year. And then T is the time in years. All right, and we can use that to find values. Go ahead and simplify these expressions. I'll do the first one with you, number 10, just so you can kind of see how your calculator is used to do that. All right, just use the order of operations here. What I would do first is do the 0.045 divided by 12 first. You can hit enter, then add 1. That's your growth rate. Now you're going to do that to the 12th power because we need to do exponents next. So raise that to the 12. And then multiply that by 1200, and you should get the right answer. So 1255.12. Go ahead and try these problems, and I'll check back with you. Okay, we're going to go ahead and do a problem like that. First thing I'd like you to do is just write down the formula so we have everything in front of us, and then identify what is represented by each of these variables in the problem, and then we'll just substitute them in and get the answer. So P is our principal, which is our initial amount. It's like our A in our normal equation. So P equals 8,000. R is our rate, and our rate is, we're going to write that as a decimal, so 3.25% divided by 100 is 0.0325. Our N is the number of times it's compounded, which in this case is monthly, so that'd be 12 times per year. And then our T is the number of years we want to do that, which is 12 years. Now we're just going to substitute all those values in and simplify it. All right, notice I simplified inside the parentheses first, and I also simplified 12 times 12, which made 144, and I ended up rounding it to the nearest cent to get the answer. Go ahead, you try that. You can check back with your answer. All right, sometimes we're going to have exponential decay, which means we're just multiplying by a number that's between 0 and 1, and it represents maybe populations that are decreasing. Here we have a population in New Haven that was 148,220 in 2005. Since then, it has decreased at an annual rate by 2.9%, and if it continues, what will be the population in the year 2015? Again, now we're going to use this formula, y equals a times b to the x. We need to know what a is. And a is the initial population, which is 148,220. B is our decay rate. Now to get your decay rate, you're going to take 1 minus 0.029. And that's whenever it's a decay, we have to subtract the decay rate. And that's because what we want is the percent we're left with, not the percent we're losing. So 1 minus 0.299, which equals 0.971. And then my x is the number of years that I'll be doing that. And so I need to do 2015 minus 2005, which is 10 years. Then I'll just plug those in, and that's 148,220 times 0.971 raised to the 10th power. All right, and if I simplify that, I get about 110,433 people. All right, you try that.
All right, that brings us to the end of the lesson. Go ahead and do the lesson check and be ready to share that in class next time we meet.